Yes, a lagging power factor is considered a power quality problem. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amperes. It represents how effectively electrical power is being used. An ideal power factor is 1.0, or unity, which means all the supplied power is being used to perform useful work. A lagging power factor, typically caused by inductive loads such as motors, transformers, and reactors, indicates that the current is lagging behind the voltage. This means that the electrical system is not using power efficiently. Firstly, a lagging power factor increases the current flowing through the electrical system for a given amount of real power. This increased current leads to higher losses in the transmission and distribution lines, as well as in transformers and other electrical equipment. These losses are proportional to the square of the current, according to the formula power loss equals current squared times resistance. Therefore, even a small increase in current can significantly increase power losses. Secondly, the increased current due to a lagging power factor can overload electrical equipment. Transformers, generators, and cables are designed to carry a specific amount of current. When the current exceeds their rated capacity, it can lead to overheating, reduced lifespan, and even equipment failure. Thirdly, a lagging power factor reduces the voltage regulation of the electrical system. Voltage regulation is the ability of the system to maintain a stable voltage level under varying load conditions. A lagging power factor can cause voltage drops, especially at the end of long distribution lines. These voltage drops can affect the performance of sensitive electronic equipment and can even cause them to malfunction. Fourthly, utilities often charge industrial and commercial customers a penalty for having a low power factor. This penalty is designed to encourage customers to improve their power factor and reduce the burden on the electrical grid. The power factor penalty is typically calculated based on the customer's average power factor over a billing period. Fifthly, power factor correction involves adding capacitive reactance to the electrical system to offset the inductive reactance. Capacitors are commonly used for power factor correction. They generate reactive power that is equal and opposite to the reactive power consumed by inductive loads. By adding capacitors, the overall power factor of the system can be improved, bringing it closer to unity. There are several methods for power factor correction. One method is to install individual capacitors at each inductive load. This is often the most effective method, as it reduces the current flowing through the entire electrical system. Another method is to install capacitor banks at the service entrance of a building or facility. This method is less expensive than individual capacitor installation, but it may not be as effective in reducing losses. An important aspect is to consider the economic benefits of power factor correction. While the initial cost of installing capacitors can be significant, the long-term benefits can outweigh the costs. These benefits include reduced power losses, lower electricity bills, improved voltage regulation, and increased equipment lifespan. When selecting capacitors for power factor correction, it is important to consider several factors, including the size of the inductive load, the desired power factor, and the voltage and frequency of the electrical system. The size of the capacitor should be carefully selected to avoid overcorrection, which can lead to a leading power factor. A leading power factor can also cause problems such as voltage rise and instability. The power factor can be improved by using synchronous condensers. These are synchronous motors that are operated without a mechanical load and are used solely to provide reactive power to the electrical system. Synchronous condensers can provide a large amount of reactive power and can also be used to regulate the voltage of the electrical system. Another method of power factor correction is the use of static VAR compensators, or SVCs. SVC are power electronic devices that can rapidly adjust the amount of reactive power injected into the electrical system. They are often used in large industrial facilities and transmission systems to maintain a stable voltage and power factor. Harmonics can also affect power factor. Harmonics are sinusoidal voltages and currents that have frequencies that are integer multiples of the fundamental frequency of the electrical system. Harmonic currents can be generated by nonlinear loads such as electronic ballasts, variable frequency drives, and computers. Harmonic currents can distort the voltage waveform and can cause a decrease in power factor. To mitigate the effects of harmonics, harmonic filters can be installed. Harmonic filters are designed to block harmonic currents from flowing through the electrical system. They typically consist of capacitors and inductors that are tuned to specific harmonic frequencies. It is important to monitor power factor regularly to ensure that it is within acceptable limits. Power factor meters can be used to measure the power factor of an electrical system. These meters can provide valuable information about the performance of the system and can help identify potential problems. Many modern power quality meters can also measure other parameters, such as voltage, current, harmonics, and transient disturbances. These meters can provide a comprehensive picture of the power quality of an electrical system. It's useful to understand the relationship between power factor and apparent power. Apparent power is the product of voltage and current and is measured in volt amperes or var. Real power is the actual power consumed by the load and is measured in watts or W or kilowatts or kW. Reactive power is the power that is exchanged between the source and the load and is measured in volt amperes reactive or var. The power factor is the ratio of real power to apparent power. A low power factor means that a large amount of apparent power is being used to supply a small amount of real power. This puts a strain on the electrical system and can lead to increased losses and reduced efficiency. Power factor correction is especially important in industrial facilities with large motor loads. Motors are typically inductive loads and can cause a significant lagging power factor. By correcting the power factor, industrial facilities can reduce their electricity bills, improve the performance of their equipment, and reduce their carbon footprint. Also consider the impact of distributed generation on power factor. Distributed generation, such as solar panels and wind turbines, can also affect the power factor of the electrical system. Solar panels typically have a power factor close to unity, while wind turbines can have a lagging or leading power factor, depending on their operating conditions. It is important to carefully consider the impact of distributed generation on power factor when designing and operating electrical systems. The location of power factor correction equipment is also important. Capacitors should be installed as close as possible to the inductive loads to minimize the current flowing through the electrical system. This can be achieved by installing individual capacitors at each motor or by installing capacitor banks at the motor control center. When selecting capacitors, it is important to consider the operating environment. Capacitors should be protected from moisture, dust, and extreme temperatures. They should also be inspected regularly for signs of damage or deterioration. In addition to capacitors, other types of power factor correction equipment are available, such as active power filters and static VAR compensators. Active power filters can compensate for both harmonic currents and reactive power, while static VAR compensators can rapidly adjust the amount of reactive power injected into the electrical system. These devices are typically used in large industrial facilities and transmission systems. There are standards and guidelines for power factor correction. IEEE Standard 519 provides recommendations for harmonic control in electrical power systems. This standard includes guidelines for limiting harmonic currents and voltages in industrial and commercial facilities. The National Electrical Code, or NEC, also contains provisions for power factor correction. NEC Section 460 covers capacitors and provides requirements for their installation and protection. In addition to reducing electricity bills, power factor correction can also improve the reliability and stability of the electrical grid. By reducing the amount of reactive power flowing through the system, power factor correction can help to prevent voltage sags and blackouts. Power factor is a critical parameter for electrical systems. A lagging power factor is a power quality problem that can lead to increased losses, reduced equipment lifespan, and higher electricity bills. Power factor correction can improve the efficiency and reliability of electrical systems and reduce the burden on the electrical grid. When designing and operating electrical systems, it is important to carefully consider the power factor and take steps to correct it if necessary. A clear understanding of power factor is essential for electrical engineers and technicians. Understanding how power factor affects the performance of electrical systems and how to correct it is crucial for ensuring the efficient and reliable operation of electrical equipment. It is also very important to be able to select the appropriate power factor correction equipment for specific application and understand the relevant standards and guidelines. Moreover, regular monitoring of power factor is necessary to ensure that it is within acceptable limits and to identify potential problems early on. Consider the cost-effectiveness of power factor correction. While the initial cost of installing capacitors can be significant, the long-term benefits can outweigh the costs, particularly in industrial facilities with large motor loads. In conclusion, a lagging power factor is undoubtedly a power quality problem. Addressing this issue through power factor correction is essential for optimizing the performance, efficiency, and reliability of electrical systems.